Alright, so this is a re-record of Problem 79 in David Altessi's collection of 100 geometry problems from AME level to USAMO, and I've made it to early USAMO stuff. So let ABCD be an isosceles trapezoid with AB parallel to CD. Yep, we got that. The inscribed circle omega of triangle BCD meets CD at E. Right, so it's an in-touch point. Next, F is a point on the internal angle bisector of DAC, such that FE is perpendicular to CD. All right, that's all well and good. And lastly, the circumscribed circle of triangle ACF. ACF meets CD at G. So our goal is now to prove that triangle AFG is isosceles. So I'm gonna pull up the paint and we will begin. So there's a few things worth noting about this diagram. It's that there's a lot going on. That's pretty clear, but you know, gotta point it out. So I solved this a bit ago, but it takes a while, so I will build up to it. And this is how my proof goes. Do note that this intersection point is not necessarily... Hold on, let me get a better diagram. How about... Okay, yeah. So we got our diagram. Firstly, I'm going to do the following thing, right? I'm going to find the incenter of triangle ACD. Now that seems completely irrelevant to what I'm trying to do, but it will make sense. So I'm going to draw the angle bisector here, and it's going to be like maybe here-ish. So I'm going to label this point here. Actually, I'm going to do this on a new layer so I can easily toggle it on and off. I'm going to label this point here I prime, okay? Now, there's a few things worth noting. Firstly, it's that, in-center, x-center provides some pretty nice lemmas. Notice that the circumscribed circle of ABCD, right? Isosceles trapezoids. Any isosceles trapezoid can be inscribed in a circle. So that's why I have the circumcircle here. So the circumcircle of ACD, right? This angle bisector here hits this point. Now, there's another thing about this angle bisector in particular. It also is collinear with B and I, right? Because the angle bisector of DAC splits arc CD into two equal sections. Same with the angle bisector of DBC, so therefore they must coincide at the same point. So that's a pretty easy thing to show. And well, clearly, the very nice lemma is that if we call this point L, since it's the intersection of the angle bisector and the circumcircle, we know a few very nice things. LD equals LC equals LI prime, okay? So that's going to be a very nice result. So we have LD equals LC equals LI prime. Second thing to notice, right, is that the following also holds. Look at angle DI prime C. With some relatively basic angle chasing, you can conclude that it is 90 plus DAC over 2. Likewise, DIC, right, this angle here that I'm highlighting right now, right here, is 90 plus this angle over 2. But this angle and this angle are the same by properties of cyclic quads, which means that this angle and that angle are the same. And this is a sufficient condition to show that D, I prime, I, and C are concyclic. But remember, L is the center of the circle that contains D, I prime, and C. So that means I must also lie in the circle. And because of that, we also have Li prime equals Li. Okay? Now, next thing worth noting, take a moment and notice that this angle here, right, is the same as this angle. The reason is because these angle bisectors, right, DI prime and CI, bisect the same angle. So those two angles are the same. But we also know that the angles opposing, since this is a cyclic quadrilateral, add up to 180. So these two angles are the same. Moreover, this thing is an isosceles trapezoid, which means that I prime I is parallel to CD. Okay? So if I undo some of the lines here and sort of bring this layer down, right? Let's look at some more lines, right? Let's look at I prime I, since that's a very nice parallel line. Now, remember, another thing worth noting is that IE is perpendicular to CD, and remember, FE is perpendicular to CE. Because both of these are perpendicular to CD at the same point, IE and F are collinear. So what that allows us to say is that this angle here is a right angle, since we showed that I prime I is parallel to CD. Okay? Now, if I completely remove this bit, right, and then I draw my I prime again, oops, draw the I prime, and draw this, right, we know a few things. We know this is I prime, we know this is L, and we know these two large segments are the same, and we know that's a right angle. Okay? Let's do some work here. Call this angle alpha, right, because this is isosceles triangle. This is 90 minus alpha, and this is 90 minus alpha. So what we can actually say is that this A is congruent to this, is congruent to that, right? That seems pretty nice. So what can we say about that? Well, there just so happens to be a really, really nice lemma called in-center x-center. And if you don't know what it is, look it up. It's probably like on a page by Evan Chen or something like that. But, you know, it exists. It's pretty nice. So that means F is the AX center of triangle ACD, right? Which allows us to conclude that this is an angle bisector, okay? Very nice. We know that this angle is equal to this angle. That is a very, very good place to be in. Because now, what you can do is take FD, right? Look at FD. FD is really nice looking here, because we know if we extend this line out, we know that this angle here, for the sake of completeness, I'm going to label a point here. How about D prime? This angle is equal to this angle. Angle D prime DF is equal to angle FDC. So now, sorry. So here's the next step, okay? This is gonna be a little crazy, but let's look at this angle here. Let's look at this point here. I'm gonna call it O for suggestive reasons, but if you look at O for a bit, you might notice something pretty particular about its placement within this configuration. Yes? Now, it's pretty crazy, but, you know, it's gonna work out. Firstly, I'm gonna draw OA, and I'm gonna draw OC. That's not a straight line. I'm gonna draw OA, and I'm gonna draw OC. Yep. And I'm gonna draw AC. This triangle, don't let its pretty nature fool you. It's not equilateral, but we can show some even nicer things about it. Notice that ODC, by nature of cyclic quads, is equal to this angle. Notice as well that angle AOC, right, is going to be 180 minus ADO, in other words, D prime DO. So this angle is the same as that. But since this is the same as this, right, by nature of cyclic quads, right, O, C, A, and D are literally concyclic by definition, we have this angle is equal to this angle, and so we have OA equals OC. All right? And that's a really, 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 really good start. Okay? Now, I'm going to continue a little bit with some tomfoolery, as they say. So I'm gonna draw segment DL. So firstly, I'm gonna redraw our findings. We have this line segment here, which I will now proceed to keep throughout the rest of the computation. So look at this. We have our point. We have our point O. We have our point L. Okay. Now we have OA equal to OC. Yes. So because we have OA equal to OC, there's a few things, but I'm not going to show them yet. The next thing I'm going to say is that, remember, we have a few things that are true. We know that, D, O, and F are collinear because we defined O to be an intersection. We know that A, L, and F are collinear because L is defined to be an intersection. So, remember, in center, X center tells us that DL is equal to LF. Remember, we proved this is the X center. So this angle is congruent to this angle. Cyclic quadrilaterals tell us that ODL is equal to OAL, so that angle here is congruent. But notice triangle AFO, right, is isosceles. So we have AO equals OF in our diagram. But we also had equals OC. So what does that tell us? O is the center of the circle that contains points A, C, and F. So that means O is the center of the larger circle. And now this is where the really powerful stuff kicks in. So let's look at some of these. Let's look at some of these angles. All right. Let's do some work. Firstly, see this? Let's label this angle alpha. All right. By the inscribed angle theorem, angle AOC, as I'm drawing here, right, is gonna be angle 2 alpha, right? Think about why, it'll make sense. But that means that angle ADC is 2 alpha, right? Well, there's a bit more. We know this angle is 180 minus 2 alpha. But that forces this angle to be alpha. So we have our first step of the plan. Secondly, draw in AC, okay? Let's look at this angle here. Notice that we define AF to be an angle bisector, so it's equal to this angle. I'm going to label it beta. I'm going to label U beta, all right? Notice that angle FGC is equal to angle FAC. The reason being is because they intersect the same arc on the larger circle. So this angle here is beta. But combining that with our previous result, we have this angle is equal to this angle, which lets us show that FG is equal to FA and FGA is isosceles, and we are done.